high temperature. And then the wavelength maximum at which peak energy emission occurs. And the rate at which radiation energy is emitted depend upon the temperature. So what happens to lambda max and T? So we know that lambda max is relation, lambda max is inversely to temperature. So when I increase the current, this is going to decrease. So lambda max decreases. This one wrong. Lambda max, this one wrong. Could be this or this. But what is P? P is the rate at which radiation energy is emitted. Rate at which radiation energy is emitted. That means like energy over time. What is this? This is power, right? Energy over time, power, or luminosity of the bulb. So we know power is the same as luminosity. So the power, what happens to the power when the temperature increase, when the current increase? So the power will increase. So lambda max decreases, but then the P increases. Okay, this is C. The rate at which radiation energy emission increases. Okay, so power, again, it is absolute brightness. Okay, the brightness of the star or the bulb, the real brightness is the power. And the brightness depends on temperature so much. And this can be recalling your Stefan Boltzmann, right? L, Stefan Boltzmann, area, T to a factor of 4. Okay, so the luminosity or the power is very dependent on the temperature. Okay, question 4, same, you do ratio. Hubble constant has been determined to be 2.2. Previous data gave a value of 2.0. The age of the universe calculated from this value would be, right, T1 equals to 1 over H1. T2, 1 over H2. We do like T2 over T1, 1 over H2 into H1. Okay, then you see the ratio, how much is that one? 2.2 minus 18. Again, sorry about my speed. I forgot my pen today. 1.1. Okay, so that means T2, 1.1 T1. It's 10% bigger. T2 is the new one, is the new Hubble constant. Okay, 10% bigger. Question 5, in which one of the following situation would be a blue shift observed? Source moving towards a stationary observer. Okay, and the last one, all quasars show large redshift in the light received from them. This shows that large redshift, they are far away from Earth. Okay, so this one is related to what? The Hubble constant. Okay, and also the Doppler shift. 6 is D. The Hubble constant is 70,000. Give one reason why it is uncertain. Okay, we mentioned about the uncertainty in the distance, right? So it's difficult to state how an estimate of the age of the universe can be calculated from Hubble constant. So this one we did, what we did was V Hubble constant D, V over D is Hubble constant. And this is 1 over T. T is 1 over Hubble constant. Explain how the ultimate fate of the universe is associated with Hubble constant. Okay, so how the Hubble constant predict the fate of the universe? Okay, first thing we said is that the Hubble constant is changing. It is not exactly a constant. The constant is changing. Due to what? Due to gravitational forces. Going down. Okay, so that would affect the Hubble constant. So Hubble constant is more like the rate, right? The rate. C maybe is a bit out of syllabus now. This question here. I don't think they will ask this one. Okay. Oops. Oh, you dropped your phone, huh? You want to get a new phone already?
Go there to buy alcohol cars.
Question 3C, you want to draw your own best fit. 3C complete, not 3C, sorry. 8C. Complete the graph with a line of best fit. State what this graph shows about the velocity. Okay, so you draw a best fit line, make sure approximate equal number of dots on each side. And then you calculate your gradient for number 2. Okay, see if you get the answer sheet they give you is in a range. Okay. Okay, so use the gradient to find the Hubble constant, and then 1 over gradient to find the time or the age of the universe. So I'm going to draw my best fit something like maybe this one. One, two, three, four, five, six, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, roughly 25 on the bottom and 23 above. Okay, PC is given, change to meter, 3.09, 16. Okay, so that's my gradient. It is in second minus 1. That's the Hubble constant. And then we change to 1 divided by this one. We get 4.64 into 1017 second. Okay, acceptable range is 4.0 to 5.2 times 10 power 17. Okay, depending on the marks lah. If they give like 1 mark or 2 marks, you can take the easy points to get the gradient. If they give like 4 marks or 5 marks, then probably they want to see you take other points, okay? Like the more complicated ones. So depending on the mark given. Okay, so we left like about 9 minutes. Just want to give you a summary on this one. Let me do. It's kind of like a framework or like a mini mind map for the whole chapters. A quick one, summary of the entire astrophysics chapters. So we start off with like what we can see. So we can see one thing is the radiant flux intensity. Okay. Let me adjust this smaller. Okay. And then given the equation for this one, F equals to luminosity over 4 pi d squared. And then what else we can see is we can see standard candle. So again, standard candle is objects that we know the luminosity, right? We got 2 types. So type 1 is supernova, and we got the Cepheid star. These two are the 2 that we learn. We can get the luminosity from these 2. So that means these 2 is related back to this luminosity here. Okay, so we can get this L from here. Then we also can see the maximum lambda max. All this we measure from the Earth, right? So maximum lambda of stars, and is related to, we can, once we have the maximum lambda, we can find the temperature, T. And then using this temperature, we can also find what? The Stefan-Boltzmann. You have luminosity is 4 pi Stefan-Boltzmann, and then R square T4. Okay, so we can relate to this one here. And again, the luminosity, you can also relate to my standard candle, this one. Okay. And we can, from the Stefan, we can get the R, the radius of the star. Okay, what else? The most recent one we got also, we can see the change in the lambda. That is from the Doppler. Change in lambda, change in frequency, the redshift, which happen to most galaxies. And equation, so you have change in lambda over change in frequency equals to relative speed over c. Okay, the main purpose of using this is to get the V lah. So get the V, and the V you can also relate to Hubble's law. This V, once we get the V, okay, most probably you're asked to find the distance. V equals to h, not distance from the Hubble. And then this distance also can be come to here. This distance here. Okay. The distance of galaxies, of stars, can also come to here. Okay, that's it.